Let's see, for example,
also have two changed. But that's so.
have fun. All right. So our the fourth and the last lecture, but not definitely the least lecture for today, is going to be the lecture by Marco Battagleri, who is going to tell us about AI methods for data analysis.
Okay, so first of all, let me thank the organizer, giving me this opportunity to share with you my thought about the AI, use of the AI, in particular for real time data analysis. This is, kind of hot topic, in particular applications for the electron collider, but not only. So I want to share, first of all, with you the reasons why I put together mainly two subjects. Okay, one is about the stream readout, the way how we are expecting to collect data in EPIC, and the other is about AI. Since you know, AI is it's a rapidly evolving, and there are a lot of people involved in AI, in particular data scientists. Not really many physicists so far, but the number is increasing. Both theoreticians and experimental physicists. And the reason why, this is my own opinion, is that physics in some way is trying to face problems in a completely different approach. This is the reason why I think that AI was not used so far, or so widely spread in the physics. It started and now seems to be one of the, let's say, one of the tools that people is using. But this the idea of the black box, that you have an input and output and you don't know exactly what happens in between, is exactly the opposite the way we, as a physicist, we think about problems. We try to, the reductionism approach is try to reduce the problem, whatever complexity it has, in first of all, identify, the main ingredients, the main points in the problem, try to get rid of all details, and then try to squeeze and find the simple roots behind, say, underlying laws or whatever behind the problem. And this is exactly the opposite as AI is approaching the problems, where you just give an input and try to get what the underlying law is without trying to, to minimize or. And I will show you a couple of examples in that, AI at the end of the day is just finding exactly what you as a physicist probably could, just thinking about the problem for half an hour, you can get the same solution in a much more efficient way. So, again, why then I'm going to give you an AI talk or AI-related talks, and what is the advantage for you? I'm an experimental physicist, so I have my main focus is not about data science, it's about physics, about experimental physics, detectors, and physics behind that to try to understand the nature's law. And I'm not, particularly expert in neither in coding, in programming, or in AI and machine learning tools. And I'm also, a little bit skeptical about AI. So again, why this should be, an advantage for you to have listened to for this lecture. I think that there are, a couple of things. First of all, this is let's say, an unbiased point of view, or biased, let's say, on the other side. It's always good to understand your enemy, to understand the reason that he has. And also, I may provide, a simple and basic picture of AI as a tool for what we are doing, with the spirit and with the idea that this is a tool. So it can be, like another tool that we are using many different ingredients in our physics analysis to extract physics. But I want to keep the focus on physics, on what the ultimate goal is, not playing with AI. And this is a different business that may be absolutely interesting and valuable, but not as a physicist. I'm really interested to use AI as a tool. And also, I'm not going to go in, in too many technical details, hoping that my audience is going to be, you know, by practitioners that are not expert in AI. So sorry, really upfront, begging your pardon in case I'm going to repeat or telling things that seems to you obvious or stupid or, you know, basic. But I try, you know, to assume that what we want to do is really establish a common language. So I'm going to start from scratch, not going, you know, with fancy or complicated AI algorithms or implementation. Will be very simple, very possibly, you know, understandable from point A to point Z. And this is exactly the way how, I decide to split and share the 3 hours that we have. That is not much if you think about it, because we have to touch, you know, different points that are, each of them could be, you know, an entire course. So it's very difficult to condensate in a few hours. I'm going to start from the basic, again, from the physics, let's say, problem, that is the data acquisition and the way how we want to use and transform the particle detector signals, and the way how AI can help in that specific problem. And then tomorrow I'm going to go through more, let's say, details, just the basis again, the basic information about AI. AI, you know, is an infinite field. I'm going to touch really, you know, scratching the surface. And then what we'll do on Wednesday is going through an example. I mean, line by line, really following the program. This is available on Colab, so you can connect and play and change and try to see together, you know, the different steps and why. Just you know, renewing or discussing things that were presented on Tuesday, but you see an application on Wednesday. Just, you know, the basic idea. If not, again, I think that just applying a code can be, again, I'm against the idea of the black box, that you don't know exactly what's going on. At least we should have an idea. The mathematics behind the data science is very complicated. It's not trivial at all. So I don't want, again, to give you nothing, you know, a deep understanding of that, but at least knowing more or less what we are doing. This is, I think, the minimum that we should require as a physicist, again, and no as a data scientist. Okay, so the resources that you can you are, you know, suggested to look at, there are, you know, both very classical books in experimental nuclear and particle physics that, despite the fact that it's probably 20 years old or 30 years old, still have, you know, the basic ingredients of any detectors. As Rosie presented today, you know, 90% of what she was talking about, other than, you know, the technology, specific technology, but the basic concepts are very well described in the Leo experiment, in the Leo book. And also, I suggest to read the EPIC streaming computing model that is specific for the EIC detector we are planning to build in the future. As far as the AI part, there are, you know, many books available. Again, this is just, you know, a sample of what I read, but many of them are very well explained and give you the basis for that. I also have to give credits to people that worked, and you know, part of the material I'm going to present are grabbed by seminars, by presentations, by other, you know, lectures that other people did. As usual, we are, you know, working with the rest of the world. We are not alone. So I'm trying just to, you know, to put in my own picture, but with the material that is available around. In particular, you know, there are a group of people working here at Brookhaven, and also other people that allow me, for instance, to set up the Jupyter notebook and the specific example that we are going to go through on Wednesday. Okay, so let's start with today's not, you know, AI will be just giving you an overview where we use AI, but let me start from the physics problem. So we would like, you know, to push the button and say, discover the heats, and AI discover the heats. Unfortunately, today it doesn't work this way. we have a, a long chain that connects the signals you get out of the detector to something that you can, look at. You have to take these signals, amplify, you have to filter them, you have to put together, you have to identify your particles. At the end of a long, long list of actions, you are able to identify, if ever, if possible, you can select the heat particle. Okay, same thing for all experiments in nuclear and high energy physics. More or less complicated, more or less, let's say, sophisticated, but exactly the same chain applied to any experiment. On the other hand, there is kind of simplicity, because an elementary particle can be characterized by only a bunch of what they call features. So we'll see that this nomenclature in AI tomorrow, but the features are, the characteristics. So particle position, particle momentum, particle mass, so you identify the particle. And at the end of the day, a detector is always providing three information: the position, the time, and the energy. These are, again, universal. Any detectors, more or less sophisticated, more or less complicated, always you get these three information. And this information can be usually are produced as an analog signal. That is not always true, but let me say that it's largely true. You start with an analog signal that leaves so with shape, with and height, with length of the signal. And in some way, you go to a digitalization of the signal, where you lose part of the information, obviously, but you gain, on the other hand, the fact that the digital signal, being less dependent on the shape, on the length, on the height of the signal, can be easily coded, and then can be, let's say, moved forward in your analysis chain in a simpler way. On top of that, a computer likes, let's say, digital signal. But this was, even before the computing or the wide use of computers, people invented a way to, they again, physicists, that they had the idea that probably moving from a signal that has some complication to something much easier, like us, can be a good choice. And actually, there are a way that the precursor, in some sense, of the idea of the bit. You have a pulse. A pulse can be defined with positive, with like a square, a rectangular square, like this one. You see here, you can define a pulse, negative, positive. You can play with that. Not necessarily a bit, what we consider now bit in a computer. And there are also, a lot of different devices that, in particular, buses, the way how the signals can be transmitted and transported, and so the different let's say, filtering or reduction that you can imply, it's hardwired. You have modules that made in the past NIM standard or VNE standard still used, pretty used, or VXS. Anyway, you have a bus where the information goes through. You have your signal. You modify your signal. You have specific modules that do for you the amplification, the filtering, the transformation of the signal at the end to get something that you can use. And nowadays, the way how you transform an analog signal to a digital signal is using digitizer. Digitizer, you sample the signal. Here it is. Again, this is pretty general. You see, you have a signal that in this case is like an exponential rise and then exponential decay of the signal. This is pretty general for most part of the signal you are gonna work with in your future. And the idea is to transform this analog signal in something that is digital. So, I mean, a series of numbers, and numbers are both in time, and you have samples, and here is the representation of what changes when you double, for instance, the frequency that you use to sample your signal, and the number of bits in which you encode the information. That again is related to y-axis. How good is the way you move from a smooth curve to something that it's just a step function because bit by bit is a single point. You know, there are people that listen to music and they claim that analog devices are, you know, far better than any digitalization because the richness and the smoothness you have due to the fact that the information is fully preserved in an analog signal rather than having a quantization that anyway is reducing your information. And we see also this effect of quantization in neural nets. Just to give you another example, how you move from, because in this case, you need to have neural nets that work with integer rather than real numbers. Okay, so again, if we just consider information that we want to capture from the signal, is usually kept in, you know, energy, and the energy is associated to the area of the signal. So you can, you know, integrate the signal. This is usually the charge. You have a voltage over time. You integrate and you close on the resistance. So usually it's a well-defined numbers, 50 ohm, or part of the signals you're gonna use, and the outcome is a charge. A charge is the energy that the detector is depositing within your, either if it is a tracker or a calorimeter. Again, this is exactly the same procedure, the same thing. For time, that is the second feature that we would like to extract from a signal, is a little bit more tricky. This is not enough just to calculate the integral or something that is, you know, well defined. Then there may be approximation in the way how you calculate the integral, but at least the idea is clear. You have to calculate the integral of a curve. In this case, you know, time definition for a signal that has a shape is not trivial at all. It depends on how the shape is. You know, it's like it's difficult to define. And the way how time is defined for a signal is always connected with the threshold. Okay, so you decide that it is the simplest thing you may imagine. When the signal is higher than a certain value, threshold, then you say, this is my starting point. When the signal goes down and lower than a certain value, then you get the end of the signal, let's say, or the end, the time that corresponded to the signal. So again, you see how an analog signal lose information. I mean, when you digitize the signal, you lose information. And again, even for this simple operation of putting a threshold, this is not trivial at all, because, for instance, you may have a problem in this way, that if you define two different, I mean, the same threshold for two different signal that has a different height, you get two different numbers, two different timing that you don't want, because, you know, I like to characterize my signal when it comes, independently on if it is high or small. I mean, there's something wrong with that. And so there are people who were clever in the past, that they did some trick in particular. You can also define not really a fixed threshold, but you can take a certain percentage of your signal. This is the constant fraction discriminator, how it works. Okay, and it is mitigate at least the problem. You always get the same. If the signal, if I put my threshold at 50% of the height of the signal, I'm going to get the timing better defined. With respect to the other case, that is giving me something that changed as a function of the charge. I mean, the time gets smaller and smaller if the signal is, let's say, is bigger. You can correct, obviously, you can do that, but you know, it's a complication. Now you have your signals. Now you have to decide if you want to keep the signal or not. I mean, you have to, in a data acquisition, any chain you may imagine, you have to decide if the signal that you are seeing is interesting or not. How you can do that? I mean, people, again, that worked for tens of years, had this idea that you can trigger the acquisition with a well-specific signal from the detector, assuming that you have, like, you know, opening up a window at a certain moment when you know the sun is going through. You don't need to keep the windows open all the time, because the sun is not exactly in front of you. You know, it's going right on the left. You only open up the window when you know that the sun is there. And this is the idea of the trigger. So again, this is a clever idea. It is you know, smart, because you can reduce. I don't need to stay all the time with my window open. I only open the window when needed. But the problem is, for the triggered acquisition, that you need to know in advance that you want only to get the sun when it is in front of you. If for any other reason you want also to get the bird that is, flying in front of the sun, but not necessarily when the sun is there, it is very complicated. You have to change your trigger. You have to change your condition that open up the window and take your lead. So this is the main reason why trigger acquisition is not, bad from the point of view of the efficiency and the speed, because this is probably the best way. If you know exactly what you want, this is very similar to ASICs compared to, or FPGAs compared to other hardware or other, systems that are multi-purpose. If you know exactly what you want, obviously you can optimize your algorithm, and you do better than, using a whatever CPU to do the same thing. So comparing CPU to FPGA or comparing an ASIC to a general purpose, let's say DAQ that gets your signal. The problem is that you need to know upfront exactly what you want. If you know that, it's perfectly fine. Obviously, you can imagine that growing up with big detectors with multi-million channels is very difficult to know from the very beginning what you want. So people invented, different level of triggers, and you can here have a kind of an example again based on tracking. You have your track that goes and hit cells or the pixels or whatever system you want to consider here, plus noise. So pixels are not aligned very well. You have hit here and hit there, and then a possible way to define the interest for a good track with respect to dust noise could be, for instance, step 0. I just want something where I have hits. If I don't have hits, it's totally useless that I get the information. Level 1. Or I get, a couple of hits, but hits needs to be close by, because if they are too sparse, too distributed over, how can you distinguish this hit from the noise? So you may define a second level that define the request that you have to have a cluster, a collection of hits that sits close by. Or you may have, at the end, very last level, when I do my analysis, I go through all my data set, I use the level 3, defining the entire track. Okay, I have clusters, I see, collection of points, and I only take and I consider for the final reconstruction to fit to my preferred way to understand what was the momentum of the particle going through the magnetic field. I'm only using the ones where I have, a good chance to reconstruct the track. Okay, you see, so there are different levels, and this is what the LHC experiment, Atlas and CNS, together with LHCb and Alice, did so far. Just a couple of years ago, they switched the paradigm and changed to a different option. But consider that this is, so far, if you know exactly what you want, it is a very effective way to proceed. So we move from, let's say, triggered data acquisition to something that is streaming readout. Streaming readout, what it means? It means simply that you are not considering anymore an information that you provide to a trigger logic that tells you, open up the window because the sun is coming, but you consider your windows, completely independent. So you can, each window that you have in your house is opening up, closing based on information that rely only on the information that you get out of this window. You don't need anything else. Obviously, this is not very efficient. This requires a lot of, information that is useless information that needs to be streamed out on the network. But has the main advantage is the flexibility. The idea that you don't need to wait for any information, an external information that usually is based on the same set of information you start from to decide if a channel is interesting or not. You just move all information you have at the next step, at the next, let's say, level. When all the information from the detector is converging in a single place, it is called the time frame builder, and where you finally can decide if the information you want to consider is interesting or it is not interesting. And the way how you recollect all this information that comes from independently from many different channels is that you attach it to each information a timestamp. So this is the way how you do, rather than doing upfront with a window and you only take events that sits within this window, you use at the end the time information that you attach to each data to decide if they are belonging to the same cluster, let's say, or to the same, they are, let's say, correlated in time. And again, you can imagine that this is obviously much more flexible because I can decide if I want to take an example very simple, the decay of a muon. The muon decay in, what's the lifetime of a muon? 1 hour, 1 year, 1 microsecond, 2 microseconds, 2.2 microseconds. So for fast acquisition, 2 microseconds is a huge amount of time. Okay, so usually if you want to get, if you have a start and say, okay, I have my muon going through, and then you want to see the effect of the decay of the muon, like for instance, measuring the positron or the electron that comes from the decay of the muon, then you need to really wait for a long time. And in between, if you have a collider, if you have an experiment, then you may have a lot of hits that may mimic the closing of the window that tells you that you are looking at the muon decay. So usually take the windows where you consider an event, so something correlated in time, much smaller. Okay. Now with streaming readout, this is almost for free because you can change a line of software and say, let's open a window of 100 nanoseconds. Now let's open a window of 10 microseconds and try to see if I have clusters that are, small in time and they define the start, and you have another cluster that defines in the end. And this can be done, just changing a line in the code rather than doing a complicated business with the wired way that the trigger requires to act and to select only decay of the muon rather than everything else. Okay, so it's clear that this is streaming readout is much more powerful. So this is one reason, and the other reason is that you have, if you want to cope with very high rate, assuming that you are able to, to move, to stream all this data from one point to another. But we are living in the internet time where you can take advantage of all progress that you have on switches. I mean, network switching. And this is exactly the same problem. What does it do? TCP/IP, exactly the same thing. It's making packages and streaming them out, and you have on the other side a socket that gets this packet and put together in what you are transmitting. Same thing here. So you can, in some way, copy, or you can use the same technology that is used in networking, taking advantage of that, of the rapid and the massive evolution of networking. And also, again, this gives you the opportunity to not think upfront how you want to optimize your data acquisition, but you give you the chance to do that at the end of the chain when, and if you want to change it, it's very easy to change. Assuming that now I want to add another channel to my acquisition. If I have, certain number of lines going in my board, and I want to add one more, I need to buy another board, and then I have to integrate the second board with the first. I mean, it's complicated. While for a switch, very well. I mean, if you have one switch, you can, just add another board or another switch close by, and this is, for free, mainly. It's not very complicated. Exactly the same for the streaming readout, so with the same logic. And on top of that, you can use high-level languages to program your program, your trigger definition. It's not necessary to go low level, like programming an FPGA in Verilog, or the languages that are, typically mastered better by engineers rather than physicists. So this gives us, some more freedom in playing with the conditions that we want to apply. And also, in principle, you can use a powerful tool like AI. That, again, is not impossible to implement on low-level hardware, but it's much more complicated. While here, again, it's almost for free. You can reuse all the technology developed for other, to drive a Tesla. You can take part of it and use it in your own problem. So obviously, it is a big advantage. And there, on the other hand, this experiment, like LHC experiment, now Alice is running the TPC they have in streaming mode. So they are, really getting all the information, and they are processing offline, where offline semi-real time means that they are, reducing the quantity of information to something usable after that data, not at the same time, or they are not selecting upfront what they want. They move everything back, and then they decide in some way which one is interesting, which one not. Same thing for For LHCb was a precursor of that because they have a problem of rates. They need to cope with the high rates, and the only way to cope with very high rates is to use a streaming readout that again work in some sense in parallel with the parallel streams rather than going, in steps. And the same for other experiments, not only at CERN, but at FAIR, for instance, CBM, DAISY, two-photon exchange experiment, but also in US, like FRIPS, Creta is using it. And BNL S-Phoenix just, had a kind of hybrid model for the streaming readout that is partially streaming and partially triggered. And for the future, EPIC is for sure is going to be streaming. So this is something that anyway is going to take place, if we like or not. And again, I'm not going to go through all the different steps, but you can really consider the way how you move from the information from the front end, so from your detector, up to the end when you have, each line are independent. At some point, you have this so-called the time frame builder where all the information, all the lines goes on and you have a switch mainly that open up the packages, look at the timestamps and put together all events that have the same timestamps in a time frame within, a certain time window. And that time window is then streamed to a node. If you have too many events, close by, you just reduce the window and stream the previous single window, you split in two and send to two nodes. So in principle, you can take advantage of this multiple processing offline or real-time analysis of your data, much better than in traditional way where the information you have to provide to the trigger needs to be hardwired and very efficient if you want to cope with high rates. And again, here is the place where AI can enter in each of these steps. I mean, moving from the information that you get out of the detector up to the building the time frame or even processing your data. So go ahead.
Yeah, I just have a question actually. What does the dead time look like?
Sorry?
Dead time for streaming readout.
There is no dead time. It's virtually zero. Virtually.
Yeah, like how does that work actually? Because
Yes, I mean, the point is that assuming that you have a circular buffer that produces data continuously, something enter, you keep for a little while, and then you put out continuously,
I see.
This is the way how, and then if you can cope with this, flux, this continuous stream of data, it's fine. The problem is at some point when you have all this stream that needs to be selected. This is the tricky part where you need to have, a powerful machine or a powerful CPU or an FPGA. But this is exactly what the switch is doing. It is not much different from that. So you can take advantage of what the switches are doing. They can master gigabits per second with no problem. And we are talking, the entire EPIC is expected to produce 100 gigabits. The entire detector is producing something that with the current technology, not in 10 years from now when EPICs will be built, but now you can easily cope with. So it's, again, this is a good connection, good synergy between particle physics, so our own problem with a technological evolution that is completely independent, obviously, from physics. This is driven by totally different reasons why people want to have, rapid connection. They want to watch soccer on TV rather than getting data. But this works. I mean, for us, we can take advantage of it. Again, so this is the scheme that we have for EPIC, and probably is even better to see here how the plane, since you have to cope with a huge stream coming from each channel, what you want to do is, if possible, reduce as much as you can the information. Try to avoid, the streaming readout is democratic. You don't have someone that tells you what you have to do. It's just moving forward your information. So it means that you are not allowed to have an input in between that say, this is interesting, this is not interesting. Good and bad. Good because, again, if I want to add another stream, it's not a problem. Bad because probably 99% of what I'm trying to stream is totally useless. Okay? So the trick here is that to reduce the volume that you have to move around on the network, since you don't have upfront an idea if the information you are taking is interesting or not, unfortunately, you have to move everything forward. And this, the only way to mitigate, if you don't have other ways, is to compress your data. And we will see exactly the application of this data reduction applied to a waveform. I have, my digitizer produce a waveform, and the way I can reduce the traffic on my network, and so the quantity of information I'm moving, is to compress the data. If I'm able to do that, I'm not losing anything because I'm not selecting if this wave shape is waveform is interesting or not. I'm just compressing, and hopefully if I see that if I want to analyze it, I can reopen up and decompress. And this is exactly what we are looking at in the example we are going to describe later on. Okay, so where AI enters in all of that. Okay, it's mainly everywhere. In principle, you can. The streaming readout has the advantage that moving let's say the border between the hardwired and hardware to a different place, you don't need to have dedicated boards. In principle, you can use CPUs, again switches. You are agnostic about the transmission, exactly the same as a network. You don't know what's inside the packet. You just move packet from here to there, and that's it. And so, same thing here, you move data back at the back end, from the front end, you move to the back end, and here, when you do the time framing, finally, you decide what is good, what is bad. I have to say that for ethics, with the numbers we are talking about, the idea is to, even if in principle we are able to do a real-time analysis, so in principle we'll be able to decide, define the time frame and decide if an event or clusters, let's say, belonging to the same time frame are interesting or not. The idea is to keep a copy of all time frames. We are not planning to dismiss anything. I mean, we want to get everything written on tape, even if you can do real-time analysis. And this is, again, with the rates we are talking about, is feasible. Alice, so far, is not able to do that. They have to take this data, because the TDC is producing, they have windows of tens of microseconds. So you can imagine a lot of information. And again, most part is totally useless. So they need to run a semi, let's say, real time. They have a buffer where they store data, they process data, they get rid of all the noise and keep only the information and save only this information. This is the way how, for instance, an experiment at CERN is working, not for the EIC. So the advantage of AI in this respect is that if you have for instance, you can easily adapt it to changing conditions of the experiment. If your threshold for any reason changes, if the system is smart enough to say, okay, I'm understanding that something is changing in the condition of the experiment, and then I will react to that. It's a kind of feedback. It's a clever or smart feedback. You can identify real-time features that you are interested in, like clusters, for instance. Assuming that I'm interested, I just want to get two gammas. I will show you an example where we were looking for pi zeros. Pi zeros is made by two gammas, so by two clusters in a calorimeter. If you get a single cluster, I mean, pi zero may decay with two gammas going very close by, but there is no way to reconstruct as a pi zero, so you don't care if you have a single cluster. So you are trying to identify double clusters, and this can be done, very easily. On the other hand, if I have to do that in a traditional way, I need to know exactly where I'm looking for, where I'm cutting my data to identify. And I will show you that there are conditions where this cut that is rigid and the hard cut, shortcuts around the mass of the pi zero cannot be done because data you are collecting from the detector are miscalibrated. So you don't know exactly, the energy scale. You don't know exactly the angle where the two clusters are produced. And so, I mean, it's very difficult you have to, usually the reconstruction of the pi zero mass happens at the end of the entire analysis, not at the very beginning. Again, here, AI, I will show you that can help. Or you can try to use data to extract the calibration constant, and then you fill in we inject in the stream in order to have something that immediately gets, calibrated. If you see something changing, drifting in time, you can, compensate, you can correct. This is a feedback. You study in electronics. This is, very simple, but the feedback usually is applied to a circuit. Here is the feedback applied to an entire thing. This is the only difference. It's not much than that. Or you can also define algorithms taking advantage again of all libraries developed for other purposes. All the programming Python, using Keras, using the PyTorch, whatever. The other, the significant work that people did for other reasons, and you can take advantage of to work on CPU, on GPUs, on FPGAs. Again, it's not impossible to do that real time. I mean, with the trigger configuration, but it's much, much harder. This is, almost for free. You can do that. You can code in a few minutes. You have your. I will show you the autoencoder we wrote to compress data. Is going to be, couple of pages of Python. So it's simple, at least conceptually. There's nothing fast. So I'm gonna, in particular, reconstruction, fast inference, calibration, and data reduction. And this is in particular, data reduction is the one that I want to stress because this is, really necessary for streaming. In case you are producing too much rate, the only way is to reduce the information you are transferring. And this is, where enters the compression of your data and then the autoencoder that I will show you Wednesday. Here are some examples of each of these categories. Like I already mentioned the Pi0. You see here, we ran an experiment. You had a calorimeter made by tungsten crystals. We identified the two clusters and we tried to reconstruct the mass of the Pi0. You see the mass of the Pi0 is given by this formula. You need to know the energy of each cluster and you need to know the angle of the two gammas. Unfortunately, we ignored that there were not one target, but two targets. There was, the official target and the window of the scattering chambers. So when we try offline to analyze data, we found two peaks. Why two peaks? That actually neither of them are an 134 MeV as expected. First of all, because data were miscalibrated, and second, because we were doing the wrong assumption. I mean, for particles coming from this point, we were calculating the angle, assuming that it was coming from the target. That it was a known information that we injected in analysis that was wrong. And then we got half of the peak, half of the events coming from the, the wrong masses. This was what happened. And so the question was, may we found a way to apply AI and find, and in this case, is an unsupervised method that tells me that I have a cluster, that this cluster may belong to a Pi0. Because I don't have, an example to train with my AI algorithm. I just want an algorithm that takes a pixel here and there from the calorimeter, assuming, you have an information that is how much energy is deposited in each pixel. You build up clusters and then you put all together and you identify that there are, two separated groups of events that you can identify or reasonably consider two different clusters. Actually, we did with a couple of different algorithms, k-means, we did it with the HDB scan, and at the end of the day, this is what happened real time. We were able to, running this algorithm that didn't have the information that we were looking for a particle whose mass was 134 MeV. We were just telling, did you see in data stream clusters and where they are, and then a posteriori you build up the mass of these two clusters, assuming that they are Pi0? Yes, it worked, and we got real time using AI, using the streaming data. We were able to reconstruct the Pi0, demonstrating that. I mean, obviously, we could also a posteriori, that the peak is sitting around 90 and around 100, and then you put a window and get rid of everything else. But in this case, we didn't even know where the peak was. And the algorithm was smart enough to understand that we had a couple of peaks in that point. So again, it was very successful and very useful. For another application, this is for tracking. In particular, there are gems connected with These particular gems are also TRD. They also look at the ionization released in the gas by the particle across the cell. And so there are, different steps to identify correct track. First of all, you need to identify, hits, then you have to identify clusters, then you have to identify a track. And on top of that, you also have to identify how much ionization is produced. So you need to do all these steps very fast. And so there were attempts to implement smart algorithms that did, step by step, all these different filtering on FPGAs, so on a fast hardware in order to get this information out. And again, results are, not yet the final, but reasonably good. And we hope that working on that we'll be able to do it and to have a faster reconstruction of these tracks with enhanced ionization. Or working on calibration constant. This was the example I was mentioning at the beginning. You have drift chambers. Drift chambers have, they are in contact with the atmospheric pressure. They are just an environment filled by gas, and you have wires in it. Particle cross and produce a signal. And the charge, the ions drift between the point close by, to the closest wire. Okay, because you have an electric field. So from the time from the drift time, you can reconstruct the position within the cell. Okay, this is the basic idea of the drift chamber. Obviously, if this time to distance function, or let's say correspondence, changes in time, this is it's terrible. You lose completely all the information about, you only have this time, and you are assuming to know exactly what is the speed of ions within the gas. But if the pressure changes, speed changes. And actually, this is exactly what happens, because the drift chambers have a large volume, and they are in touch with the rest of the atmospheric pressure. So atmospheric pressure goes up and down, you have a storm passing by, and then obviously your low pressure is reflected by a change in speed. And actually, this is what is reported here. This was a change of the pressure that correspond to a change of this function that connected speed in the gas to the time that you measure. Half of the drift chamber in the BlueX, that is an experiment at Jefferson Lab, half of the drift chamber was just connected as it is, and you have this shape. Not a big problem. At the end of the run, this is a kind of time, even numbers, but it's a time. At the end of the run, you say, no, I don't want any shape. I want everything flat, because the time to distance needs to be, only one function. If something changes, I know that I have to keep this triangle to something that is flat. Okay? And in blue is reported what an AI algorithm was doing real time. So in this case, you see that how AI, again, this is a feedback, nothing, particularly fancy. But as an application that show you that you can master, for instance, calibration constants real time. You can imagine that from when you take the data to the time you publish a paper, the 90% of this long time is due to the way how you transform your signal, your detector signal, to something that is, you can do the high-level analysis like momentum of particles, etc. The most part of the time you're spending to calibrate your data, to try to see if everything makes sense, and etc., etc. So if you have now a system that allows you to do it, real time, you are saving a lot of time and a lot of money, because obviously, with the same time of running, you can immediately say if something wrong and say, no, change the condition of the run. You have, this information prompt. It is much better than what we are doing so far. So again, another advantages of doing this application for calibration constant. And finally, there is the last item that we will discuss in more details in the next days. That is exactly the autoencoder. Again, the idea is that having a trigger allows you to reduce the rate of useless information, because something is triggering obviously, the drawback of that is that if you implement the wrong trigger in your data acquisition, you are done. I mean, the experiment needs to get scratched. It's totally waste. Here you have the flexibility to not, to be more elastic in defining your best trigger and your best conditions. But on the other hand, you have to move your data from the beginning to the end. Again, assuming another trick that people use in a triggered acquisition, you have different thresholds. So you can use a threshold for, assuming that I'm looking at the calorimeter information, I can use a trigger threshold that works with pretty high level, because I want to identify a gamma of a few GeV. So I'm sure that if there is a single crystal with energy deposited, smaller than 500 MeV, I don't care. This is not for sure a gamma of 1 GeV. Okay, so I have a very high threshold on my trigger that say, take data, collect and put on the disk only events with 1 pixel with energy higher than 500. The problem is, as you probably know, that the resolution of a calorimeter is not really depending on the seed energy deposited in one crystal, but at the end of the ultimate resolution depends on the energy of the small fraction that you get spread over many other crystals. Okay, so it means that when you collect the data, as soon as you know that this is an interesting possible cluster, possible gamma of 1 GeV, you want to take the 500 MeV crystals, and you also want to get all the nearby crystals, even if they have 1 MeV in them, because when you sum up the energy of the cluster of the electromagnetic shower is the sum of all energy of all crystals. It's not only, the seed. So you with a triggered acquisition, you may play with two different thresholds. You may have a trigger threshold that look at 500 MeV signal from one crystal, is the condition to get. And when you say, yes, I have at least one crystal with 500, get everything. And so you lower the threshold at 1 MeV, because you are, just collecting data for a very narrow time window around the 500 MeV deposition. With the streaming readout, this is impossible, because you don't know upfront that there is one crystal with 500 MeV energy deposit. So this forces you to work all the time with thresholds that are 1 MeV. So you can imagine how, noise, for instance, is entering in the business. Very similar, the reach, dual reach for EPIC is using a silicon PM to detect the ring. Cherenkov light is produced when a particle runs faster than the light in the medium. It's produce a cone, few photons that are distributed around, a circle, and you have photodetectors, in this case, silicon PM, that detect these photons produced by the track. The problem is that the number of hits that you are expecting from dual reach EPIC in the EPIC configuration on a silicon PM we are thinking to use is only few photons. How could you, and you know that a silicon PM, if you don't know, I can tell you, if you put the threshold of 1 photoelectrons, so you want to get the information when you have at least 1 photoelectron produced by a silicon PM is going to be megahertz. So at the end of the day, the system that is producing more data in the entire, by 2 orders of magnitude, more than the tracker that are, tens of millions of channels, is the dual reach. Because you have to all the time keep a threshold very low at the level of 1 photoelectron, and you have a 1 megahertz per channel. You multiply by 1 million, and you get, an incredible rate that dominates the entire EPIC detector. But there is no other way. I mean, you have to get all this information that 99.99999% is junk. But you have to keep it, because only when you correlate, in this case, it's more difficult. It's not only timing correlation, also a spatial correlation. You want to, get a couple of pixels close by that identify a part of a circle. Only when you do the final analysis, you can say, no, okay, this is junk, and this may be, something good, because maybe you have the information from the tracker that tells you where the particles were going, and then where you're expecting to look at your circle is produced. But this can only be done knowing the track, and the track is usually the end of the analysis, not at the beginning, okay? So you see, I mean, streaming readout is very powerful, but on the other hand, is forcing you to cope with the enormous, with the gigantic rates at the level of front end and moving on the network. Now, okay, progresses are such that if you are now running at a few kilohertz per channel, is not a big deal. Even with the current, with a very simple situation on Raspberry, you can do that. Obviously, if you are talking about megahertz per each channel and you multiply by millions, this requires much more sophisticated data acquisition. And also, if possible, all this data that in principle are, probably junk, you need to compress, you need to reduce the volume that you are moving. I mean, obviously, the size at the end of the day is a multiplication of two factors, is the rate and the size of each data you are moving. So either you reduce the rate, but the rate is not reducible because if I have my silicon PM that is firing for thermoelectric reason, not really because it was hit by a chunk of gamma, I cannot distinguish by the one when it was really hit by a gamma. So I cannot reduce the rate. And then the only way is to reduce the size of the data that you are streaming out. And this is the reason why the data reduction, and in particular, this autoencoder can be, a good choice for that. In particular, what we are going to see tomorrow, in a couple of days will be, how if I have a signal like that, you see that in principle, you can immediately extract the couple of features you are interested in. That is, I can summarize this pulse shape with two numbers. One is the time. I apply, a fast algorithm that tells me when the sample goes higher, in which sample the value was higher than a certain value, the threshold, and I got the time for what we discussed before. Or I can do just the integration of the signal, summing up the samples and take the charge. I have two numbers in place of all the samples of the signal. This works, but if you have pilot, if you have two signals close by, when you collect only the integral of the signal, you lose the information that you had two signals overlapping. And you will never discover that they were two signals if you don't get the pulse shape, at the end of the chain or the analysis chain. So this is the reason why you are relying mainly in only the information. This is another, if you like, is exactly, the application of AI algorithm that transform features that are a certain number of samples in two numbers that are time and charge, making, the threshold and making the integral of the signal. This is exactly kind of algorithms like the same as we have, but we want to do something that's a little bit more fancy, not only calculate the integral and doing this timing, but also transporting the waveform. That, for the most part of the cases, we don't need it, but in case you need it, you can always reconstruct because you have it at the end of the chain. And in this way, I will show you that you can, depending on the shape of the signal you have, you may gain up to, to order of magnitude the size of your data sample. So it's a very, very strong, but I mean, this is again, easy to imagine. If we were relying in a low rate experiment where I'm sure that there is no any pile up, you can compress all this information contained in this analog signal just into numbers. So whatever numbers, of samples you take, at the end of the day, you get two numbers. To integer, to real numbers, rather than taking all bits for each sample and then reconstruct the shape. So again, no big surprise if this algorithms is able to compress your information in extracting what they call again the features. The features are charge and time for that specific example, and compressing. And then the problem is, can I do the opposite? Can I, reconstruct it from the charge and the time, the shape? No, unfortunately, for this kind of signal is impossible. From the two numbers, you are not able to go back to the line that you started with. For signals that are, different, that are, shaped in a different way, in principle, yes. Again, this is exactly what you do when you do a fit to a function. If I know that my point sits on a line, I don't need to move, a million of points. I just move the 2 parameters of the line, 2 parameters, and that's it. And this is exactly what the AI algorithm is doing. It tries to compress, the features that you have in real world to latent space, where these features are, enough to describe, to keep the information. And then when you apply the second part of the autoencoder is using these 2 features, like I'm fitting, an exponential. Exponential needs 2 parameters. I starting from many different, shapes and other stuff. And at the end of the day, I got 2 numbers. And from these 2 numbers, I can always reconstruct my exponential because I know that this is an exponential. Okay, so the information in some way is not lost because I have, I'm adding, I know, and this is what the autoencoder is doing, is encoding the fact that I have an exponential at the beginning and then I want to have an exponential at the end in the weights of the neural network. We'll see that, in more details, but this is the idea. So again, don't be surprised that a significant gain in terms of compression is possible using an algorithm. Again, I mean, if we were, human being, you probably were using an exponent, or in this case, I know that this can be parameterized by, I don't know, a couple of functions, I know, and then I can always fit them, get the parameters, maybe not 2, maybe 4 parameters, and that is exactly the same as the AI is doing. I mean, it's not much different what we can do. Okay, so again, AI is not a magic wonder, it's, it's kind of tool that can be useful. So this is nothing against, but don't consider that as a miracle because it is not. I mean, if I think about my problem here of this problem here, they fit when they train the algorithms. The features that they were using from the drift chamber were about 50. So they keep, the position of the wires, they keep the pressure, they keep a lot of other parameters. And at the end, when they, let the algorithms to understand which one was the right parameters to train on, or let's say to supervise on, was only the pressure. That is exactly what, you as a physicist say, come on, we have a volume that is moving, the change in the pressure outside is changing the pressure inside, changing the pressure, changing the speed. So you 2 + 2 makes 4, and it's clear that the main reason why the system was changing was the pressure. But a priori, the algorithm didn't know. They just feed all the possible information from the drift chamber to find at the end, the AI found it, that the only parameter that was significant was the pressure, the external pressure, that was the one that determined 90% of this feedback and this flat line. So again, if you are smart enough, you don't even need an AI. Thank you. First questions.
Sorry, I have another one. I might have missed this, right? But I think it was in the last slide where you were talking about the encoder. So would you still, if you use the encoder, would you still be able to recreate the waveform?
Yes. This is the autoencoder. The idea of the autoencoder is that you start from a certain space. In this case, it's the space of points defining your line shape. So it's the 48 numbers in the example we are gonna work with is 48 samples. You feed it to a neural net. A neural net understands that there is a shape that is, recursive, is always the same shape, even if you event by event, you may have the peak moving back and forth, you may have the peak going up and down, but it's smart enough, exactly the same as a fit. If you have a fit and you are, you master, you say, I want to parameterize this shape with a line here, with something going up, let's say linear shape, and then an exponential decay. Okay, and these are 3 functions. You know these 3 functions, you calculate the values of these 3 functions that are probably 2 per each function. And if I know that, I can, parameterize. And when you need, you just put it back in a very easy way. I mean, you can just reconstruct exactly the line shape. So
and this would also work for pilot then.
You can train exactly. It is absolutely true. If you just use the autoencoder as it is, it doesn't work. So you have to know and to train the system, telling it, pay attention that sometimes you have two peaks, exactly the same as you as a physicist. I tell you, pay attention. Don't just use a single function. Let's try to a double peak. Let's try to see if there are two peaks in your picture. Okay, you do exactly the same. I mean, you have an automatic and let's say smart way to do that over and over and millions of samples. But in principle, if I tell you that there may be some, again, people were not expecting AI to deal with pileup. I mean, they were able to cope with that even without AI. Right. AI is a tool. It's a nice and smart and fast tool, but it's nothing else than a tool. You don't have to renounce to your intelligence, to your brain, because this is at the end of the day makes the difference. It's not AI. So you have to inject this information anyway, because you cannot just say, do it, defeat it, and you say, I show you an unsupervised, for instance, you can, you can put together different layers of AI. The first one that identify how many peaks you have in your picture, for instance, in a totally unsupervised way. So you don't need to know a priori that there are one or two. You may have 3, 4, 5, because you run your HDD scan and find, how many peaks you have your function. Again, not much different than algorithms that you may write looking at. Yeah, it's the same thing, just a little bit maybe involuted or complicated. And then you have a second algorithm that as soon as you know how many peaks, then optimize your learning curve on that. If you don't feed them in the training phase multiple peaks events, obviously you get wrong. AI gets wrong. You're using a wrong information. So again, there is no magic, no miracle made by AI. It's just a tool. A smart way to do things that you can do in other way, and you choose the best tool you have.
If you have ever written a code with neural nets or used PyTorch, TensorFlow, or anything of this sort? Some of us. I did it the first time last year. Now I'm teaching courses.
Yeah, for physics, again, I don't want to under-evaluate, because the data science is a complicated business. There are also, I'm going to touch it, some of these, fundamental, foundational, let's say, items and point in how, for instance, there is a distinction between fitting and, interpolating, let's say, and extrapolating. But again, as a physicist, at least this is I will show you, a specific example. I am sure that you cannot, data scientists, I'm going to show you tomorrow. Yes, tomorrow. Data scientists were very, very excited that the neural net was learning a certain pattern and was able to give us, the behavior of data outside the measured region. I say, come on, how, if you are not measuring, you are not measuring. There is no way to recover what you are not measuring. You have to make some hypothesis, continuity, behavior, but you have to inject this information to the system. If not, you are inventing. You may have, a smooth invention that seems similar. You have a dog, you have, a picture of a dog that is similar, but nothing guaranteed that when I try to extract the information outside the region that you really measure with your detector, you are getting the right answer. Actually, this is exactly the opposite. We are doing experiment because we don't know what happens in certain part of the phase space. If we already knew that, we are not running an experiment of a couple of billions. Why you should? You know everything. So why you should? So the problem is that, this is a different attitude. The data scientists we are working with, they were, very excited because we finally get that, an extrapolation in the region where we are not measuring. and say, okay, yes, you get it. You have a smooth function, but who tells you that it is right? You have nothing to compare with. Your physics in that specific area can be completely different, dominated by another process that you don't have. Take the Primakov effect that give you a cross-section in the first on nuclei, is a diffractive scattering at very small angles that give you an increase of the cross-section of order of magnitude in a couple of degrees. So if you never get in that area, you will say, oh, I have a smooth function that goes to zero. No, if you measure, you get an increase there. If pentaquark, you have a narrow resonance. If you don't measure that, you can say, no, I have a smooth behavior outside my resolution, outside my acceptance of the detector. But this is not what we are after. This is not, again, be very careful, because AI is meant to be, for some, like driving a car, this is probably the only way. You are comparing what we are doing with tens or I don't know, 50 years of experience of people that thought about solutions. So it's not like comparing, nothing with the AI. It's comparing a very well sophisticated approach, let's say, in the whole. I mean, I'm not specifically talking about fitting or just the approach that is, was based on years and years and years of people, bright minds that thought about it and extract information out of data without AI. So be very careful in considering AI as the result, as the final, it's just a tool,
Another way to make that kind of system resilient to failures in the future. Example, an experiment after 5-10 years, some system can start, some detectors can start behaving unexpectedly and weirdly. And if you don't keep the entire waveform, how can you make sure that you can treat those cases too and realize that there is a problem?
Absolutely, this is exactly the reason why we are considering that compressing the waveform and keeping and saving the waveform is crucial. On the other hand, every time that you define a trigger, there is the possibility that you did something wrong or something changed in the condition of the experiment, and your conditions that you thought at the beginning of the experiment are not anymore valid at the end. And so part of the experiment is wasted. I mean, there are tons of examples of experiments that failed or changing over time. You can only use part of the data you collected because part of them were so degraded by an external change in the condition of the detector that you couldn't in some way recover. AI in that sense again can be very helpful because it can be very useful because you can in principle have a feedback real time. You can compensate or know, at least knowing that something is changing significantly in the detector conditions. So can be, again, very useful, very, very effective. And then correct, because again, this is, from hardware wise, our hardware point of view, there's nothing better than having good data from scratch. It's rather than, getting junk data and then try to correct them. This is reverse engineering on data is a nightmare that is also, there are so many steps in the data analysis that this is the reason why there is also a lot of skepticism against use of AI or using streaming readout, using this fancy mechanism, because you have the impression that if something is wrong in the chain, you're really losing everything, and you don't have step by step that they say, okay, I know that this part is failing. You have a neural net. Who knows how weights are? If you start again your training, you may have a completely different configuration of weights that may work. I mean, there is there is a theorem that no free lunch that tells you that there is no way to, there is no a priori a way to say that one network is better than another, or that this is the solution for this is, mathematically or information theory demonstrated that prevent, it's also, uncertainty quantification, the way how you can associate an error to the AI prediction or even the fit is another, field that we open as a physicist. Because again, if you have just to, identify a dog from a cat, or generate an image of a dog that is, more or less what you're looking at. This is more a dog rather than a cat. You don't really need to, to be precise. Why we do stuff that we need to be precise. We want to know exactly what is the error associated to it. It's even more important the error than the value that you extract from a measurement, because this tells you how much I have to trust the number I'm quoting. So all this part is completely new for AI. And we, as the physicists, we are, now starting to dig into this problem that is quite famous.
Sorry, this might be a bit more philosophical, but when you define your buffer, right, as you're trying to stream the data, in this sense, how do you account for overlap? What I mean by that is where you can imagine, in principle now, it's very assembly-like, right? You have your trigger, and then the next event comes along. But when you don't have that, you can, in principle, imagine that there might be an overlap, right?
Yes, I think
So in that case, like,
if there is an overlap, again, this is, the information you have is lost, and there is no way to recover in any way. Even if I have an overlap, you will never know. I mean, you have to assume that the signal, the signal that overlaps, if I have a signal like that, and another signal starting here that goes this way, I have to assume that the second signal has exactly the same shape as the first. Because if not, I don't have enough, information to reconstruct the signal. So I'm using also, kind of a priori information. It's not just based on data. It's not only, based on observation. So I'm injecting some hypotheses that are, reasonable hypotheses. If they are correct or not, there is no way to check, because if I have two overlapping pulses, how can I? The only thing is that, I have to analyze a million of single events and say they always have the same shape, and then I can infer that the one after 1 million has the same as the other, and then when they overlap, I know the shape of each of them. But I have to, I'm guessing. I'm just guessing.
But let's thank. All right, now it's dinner time. We'll come back here at 7:30. This floor, we'll have several rooms for divide in groups. You know your groups. You know your.
So there'll be 5 groups. If you look at the participant list, you'll see there's a number for Monday and a number for Tuesday, because we're going to mix you up the first 2 days. And